So now let's see the parameters of a parallel tuning circuit, or characteristics of a parallel tuning circuit. The frequency at which parallel resonance occurs, that means reactive component of circuit current becomes zero, is called resonance frequency. The main characteristics of tuning circuit are as follow. That's the first one. Let's see, find the impedance. So to find impedance, number one, from this equation, IC becomes IL sine of theta. That's what we see in the previous. IC means V over XC equal to IL means V over Z1, that is the impedance of RL. Sine means what we see from the right triangle, XLR, that is the hypotenuse Z. So sine theta is opposite over hypotenuse XL over Z1. So from this one we get Z1, that is the first branch, the branch of R and R. So simplified this equation, V by V cancelled, then XC XL becomes Z1 square. So XC means 1 over omega L, simply XL means that is omega L, that is, this is omega C. So omega by omega, this becomes Z1 square Z1 square, that is L over C. So Z1 becomes under root of L over C. So this is our impedance of Z1. This impedance for branch 1. For this circuit, for this one, Z1 becomes under root of L over C. Now we need the impedance, total impedance, or dynamic impedance. That is number 2 parameter, impedance, total impedance. So simply Ohm's law, V I minus V over Z. So to find this Z, we use I becomes IL cos theta. From this equation we get total impedance, the whole dynamic impedance. So I V over Z, that means IL V over Z1 cos theta, that's the cos theta from the right triangle. From this one, cos theta becomes adjacent over hypotenuse. So adjacent over the hypotenuse, R over our hypotenuse is Z1. So let's simplify this circuit, V by V, then ZR becomes Z1 square. So Z1 means under root of L over C. So ZR becomes under root of L over C the whole square. So this means ZR becomes the root of the whole square means L over C. So Z becomes L over C 1 over R. So the total impedance becomes R over LC. Let's show you the circuit. That is L over CR. Sorry, L over CR. This when you this record L is becomes opposite. This becomes L over RC, or Z, the dynamic impedance, or the circuit of R impedance becomes L over CR. So this is for the whole impedance becomes Z becomes L over CR. This is dynamic impedance of our circuit. So the ratio of supply voltage to the line current is the impedance of the tuned circuit. Impedance offered by LC circuit is given supply voltage over line equation. So supply voltage line equation is equal to V times I. So at resonance, the line current decrease while the impedance increase. The below feature represents the impedance curve of para-resonant circuit. So to obtain an equation for circuit, let us consider line current becomes IL cos theta I over ZR, so the total or dynamic impedance, IL V over ZL cos R over ZL 1 over ZR. Then when you cancel V by V, 1 over ZR, R over ZL square over R over L over C, so C over R. Then when you the reciprocal is inverted, ZL square is equal to LC. Therefore, circuit impedance obtained L over CR. Thus, at para-resonance, the circuit impedance is equal to L over CR. So, when you see that the impedance characteristics, this is the y-axis as impedance, the x-axis as a frequency. What does it mean? So, to define this one, this is our FR, that is phasor diagram. This is our impedance, the y-axis is frequency. So this is the resonance frequency. If F less than FR, our circuit becomes inductive. If F less than FR, the circuit becomes inductive reactance, that is XL. If F greater than FR, our circuit becomes XC, that is capacitive reactance, XC. But if frequency equal to FR, that is resistive circuit, so the circuit becomes resistive or impedance, that is R. So this is the characters of the impedance of with resonant frequency. So impedance of the circuit decrease for the value above and below the resonant frequency. Hence, the selection of particular frequency and rejection of other frequency is possible. So, if F is less than the resonant frequency, the circuit acts as reactance of inductance. If the frequency becomes greater than this FR, the circuit becomes act as reactive capacitance. But if F equal to this resonance, that is resistivity, this becomes curve. So at para-resonance, the circuit or line current is given by the applied voltage divided by circuit impedance. So line current V over ZR. So ZR means the dynamic impedance of our circuit, L over CR. So because ZR is very high, the line current will be very low. That means opposite of this circuit. So the current becomes like this one. When the impedance is high, the current becomes low. When the impedance is high, the current becomes low. So to define the characteristics of impedance or line current. So what does mean quality factor? So for a para-resonance circuit, the sharpness of the resonance curve determines the selectivity. So quality, it depends on the selectivity. The smaller the resistance of the coil, the sharper the resonance curve will be. So what we see, if frequency becomes equal to with resonance frequency, that the circuit becomes resistivity. So the smaller resistance of the coil, the sharper the resonance curve will be. Hence, the inductive reactance and resistance of the coil determine the quality of the tuner circuit. So the ratio of inductive reactance of the coil at resonance to its resistance is known as quality factor. So XL over R. So the higher the value of quality, the sharper the resonance curve and the better the selectivity will be. So quality factor with the selectivity. So it is desired that resonance curve of parallel tuning circuit should be as sharp as possible in order to provide selectivity. The sharp resonance curve means the impedance falls rapidly as the frequency is varied from the resonance frequency. The smaller resistance of the coil, the sharper the resonance curve is. The ratio of inductive reactance and resistance of the coil as resonance, therefore, becomes measure of the quality of tuning circuit. This is called quality factor and may be defined as under the ratio of inductive reactance of the coil at resonance to its resistance is known as quality factor. It depended on the XL over R. That XL means to pay FR over LR. So the quality factor of parallel tuning circuit is very important because the sharpness of resonance curve and hence selectivity of the circuit depend upon it. So the higher the value of quality, the more selective is the tuning circuit. So the feature below shows the effect of resistance R of the coil on the sharpness of the resonance curve. It is clear that when the resistance is small, the resonance curve is very sharp. However, if the coil has large resistance, the resonance curve is less sharp. It may be emphasized that where high selectivity desired, the value of Q should be very large. Looking, the smaller resistance, the sharper of the curve. So we get high quality. Large resistance becomes wide or large our quality. So strictly speaking, the quality of tuning circuit defined as the ratio of energy stored in the circuit to the energy lost in the circuit. So energy stored over energy lost. So the energy lost is the reactive power, and loss the resistive power. So IL square XL over IL square. So cancel IL square. This becomes XL over R. So this is one parameter of our tuning circuit is quality factor. It depends on the reactance of inductive and the resistivity. So the following are the advantage tuned amplifiers. The usage of reactive component like L and C minimize the power loss, which makes the tuned amplifier efficient. The selectivity and amplification of desired frequency is high by providing higher impedance at resonant frequency. A smaller correct supply VC will do because of its little resistance in the parallel tuning circuit. It's important to remember that advantages are not applicable when there is high resistive collector load. So another parameters of the tuned amplifier is frequency response tuning circuit. So the voltage gain becomes beta ZC over Zin. That's what in the first what you learn when you the resistance load replaced by the tuner circuit. So the gain of that amplifier beta of ZC over Zin. But before replace it by a tuned, that gain of that amplifier is beta RO over Rin. So this R replaced by the tuned circuit. So the frequency of tuned circuit is becomes by the voltage gain of our amplifier this circuit. That amplifier is a collector or transistor type. So where ZC effective collector load and Z in input impedance of the amplifier, the value of ZC depend upon the frequency of tuned amplifier. As ZC is maximum as resonant frequency, the gain of amplifier is maximum as this resonant frequency. Another parameter of tuned amplifier is the bandwidth, the range of frequency at which the voltage gain of tuned amplifier falls to 70% or 7.7% of the maximum gain is called bandwidth. The range of frequency between lower frequency and higher frequency, that means F1 and F2, is called as bandwidth of the tuned amplifier. The bandwidth of tuned amplifier depend upon the quality of the LC circuit. That means upon the sharpness of the frequency response, the value of quality and the bandwidth are inversely proportional. So all channels or signals, it becomes reached this 70% of in tuned circuit, but cannot pass this 70%. So the feature below details the bandwidth and frequency response of tuned amplifier. So the lowest frequency reached 70% and the highest frequency reached 70%, but that particular frequency is becomes maximum gain of amplifier. So the relation between quality and bandwidth is the quality factor of bandwidth is defined as the ratio of resonant frequency to bandwidth. That means quality of, when you compare bandwidth with quality factor, resonant frequency over bandwidth. So FR means 1 over 2 pi under root of LC. In general, particular circuit has its quality value always greater than 10. In practical tuned under this condition, the resonant frequency at parallel resonance is given FR over 1 over 2 pi root of LC. So do it and practice this activity in your home and give some comments in the comment boxes. So in the next you will see about types of tuned amplifier, that is single tuned amplifier and double tuned amplifier. So types of tuned amplifier, there are two main types of tuned amplifier. They are single tuned amplifier and double tuned amplifier. Let's see one by one. In single tuned amplifier, an amplifier circuit with a single tuner section being as the collector of the amplifier circuit is called single tuner amplifier circuit. The construction of single tuner circuit, a simple transistor amplifier circuit consists of a parallel tuner circuit and its collector load makes a single tuned amplifier circuit. The values of capacitance and inductance of the tuned circuit are selected such that its resonant frequency is equal to the frequency to be amplified. The following circuit diagram shows single tuned amplifier. Look it as the collector side of the transistor, that is in the load when you connect it with parallel LC circuit, that is tuned amplifier, that is single tuned, single C, single L, that is LC parallel tuned circuit. So the output can be obtained from the coupling capacitor as shown above, or from secondary winding placed L. The high frequency signal that has to be amplified is applied as the input of the amplifier. The resonant frequency of parallel tuned circuit is made equal to the frequency of the signal applied by altering the capacitance value of the capacitor in the tuned circuit. At this stage, the tuned circuit offers high impedance to the signal frequency, which helps to offer high output across the tuned circuit. As high impedance is offered only for the tuned frequency, all the other frequencies which get lower impedance are rejected by the tuning circuit. Hence, the tuned amplifier select and amplify the desired frequency signal. That is the particular frequency or natural frequency signal can be amplified. So, the power resonance occurs at resonant frequency when the circuit has high quality. The resonant frequency FR becomes 1 over 2 pi root of LC. That is the resonant frequency when XL balanced with XC. The following graph shows the frequency response of single tuned amplifier circuit. So the highest signal we get in the impedance, that we can call it resonant frequency. So at resonant frequency, the impedance of power tuned circuit is very high and is poorly resistive. The voltage across RL is therefore maximum when the circuit is tuned to resonant frequency. Hence, the voltage gain is maximum at resonant frequency and drops off above and below it. The higher the quality, the narrower will the curve. So, look it in this circuit. We have an inductor 30 millihenry, a capacitor 0.1 microfarad. So determine the resonant frequency, the quality of the circuit, and the bandwidth of the amplifier. So to get the resonant frequency, as you know, the formula of resonance 1 over 2 pi root of LC. That becomes L is 33 and capacitor is 0.1. So we can get 2.77 kilohertz. So the resonant frequency for this single tuned amplifier is 2.77 kilohertz. So again, the quality of that tuned circuit, so the quality becomes energy store over energy loss. That is XL over R. So our XL, to find XL, so convert this one. You have a frequency, then this inductor change to reactance of inductive. So this becomes 2 pi FRL, XL minus, then our FR is 2.77. So our reactance of inductive 574 ohm. So our resistance becomes 25 ohm. Our quality is 20. So that is practically what we say. The quality factor must be greater than 10. So our quality is 20. So the bandwidth of this, the resonant frequency over the quality, so 120 hertz. That is from the highest to the lowest, from highest plus or minus this 20 by 120. So the bandwidth becomes 120 hertz. So see this simple circuit or single tuned circuit with example. When you say in double tuned amplifier, an amplifier circuit with double tuned section being as the collector of the amplifier circuit is called double tuned circuit. Look, in the previous we have seen only one capacitor, one inductor, but in double tuned we have coupling each other. The construction of double tuned amplifier is understood by having a look at the following feature. This circuit consists of two tuned circuits, L1 C1 and L2 C2. In the collector section of the amplifier, the signal as the output of tuned circuit L1 C1 is coupled to the other tuned circuit L2 C2 through mutual coupling method. The remaining circuits are sum as single tuned amplifier circuits. Only the difference in the load of collector you can replace with double tuned circuits. So the high frequency signal which has to be amplified is given to the input of the amplifier. The tuned circuit L1C1 is tuned to the input signal frequency. At this condition, the tuned circuit offers high reactance to the signal frequency. Consequently, large output appears as the output of the tuned circuit L1C1, which is then coupled to the other tuned circuit L2C2 through mutual induction. Thus, double tuned circuits are extensively used for coupling various circuits of radio and television receivers. So the frequency response of double tuned amplifier. The double tuned amplifier has special feature of coupling which is important in determining of frequency response of the amplifier. The amount of mutual inductance between the two tuned circuit status the degree of coupling which determines the frequency response of the circuit. In order to have an idea on the mutual inductance property, let us go through the basic principles. So it depends on the mutual inductance of the tuned circuits from L1C1 and L2C2, how they related both of the mutual inductance. So as a current carry coil produces some magnetic field around it, if another coil is brought near this coil such that it is in the magnetic flux region of the primary, then the varying of magnetic flux induces an electromotive force in the second coil. If this first coil is called primary coil, the second one called secondary coil. When the EMF, electromotive force, is induced in the second coil due to the varying of magnetic field of the primary coil, then such phenomena is called mutual inductance. So the same principle in the double tuned circuit of in the mutual inductance. So the coupling under the concept of mutual inductance, coupling will as shown is a feature below. So how they closely related L1 with L2? Is that far or closely? When the coils are spaced apart, the flux linkage of primary coil L1 will not link the second coil L2. At this condition, the coils are said to have loose coupling. The result from the secondary coil as the condition is small and the resistance curve will be sharp and the quality high as shown in the figure below. Look at the loose coupling, tight coupling. On the contrary, when the primary and secondary coil are brought close together, they have tight coupling. Under such conditions, the reflected resistance will be large and the quality is lower. Two positions of gain maximum, one above and the other below the resonance frequency are obtained. So by this principle, the double tuned is on the principle of coupling or mutual inductance. So what are the boundaries of double tuned circuits? As the above feature clearly states that the boundary is increased with the degree of coupling. The determining factor in double tuned circuit is not quality but the coupling. We understood that for a given frequency, the tighter the coupling, the greater the bandwidth will be. The equational bandwidth is given as the bandwidth of double tuned circuit becomes K multiplied with resonance frequency. So K is a coefficient of coupling and F is the resonance frequency. So when you see in this example, the bandwidth is 200 kilohertz and the resonance frequency becomes 10 megahertz, determine the coefficient of coupling. So bandwidth becomes this equation, so the coupling of coefficient becomes bandwidth over FR. So 0.02. That is coupling of coefficient. How they closely related? Is that far or close? Is that space or tight? That is coupling of coefficient. Practical application of double tuned amplifier. Double tuned amplifier are used for simplifying radio frequency signal. One such application is the radio receiver as shown in the figure 2.61. In the next feature, this is the IF or intermediate frequency stage using double tuned resonance circuit. Each resonance circuit tuned to 455 kilohertz. The critical coupling occurs when the coefficient of coupling is becomes 1 over under root of Q1, Q2. So for Q1 means qualified primary resonance L1 C1, Q2 means qualified resonance secondary L2 C2. So by this means we can get coupling coefficient and also quality factor. So when two resonance circuits are critically coupled, the frequency response becomes flat over considerable range of frequency as shown in the figure 2.7. In other words, the double tuned circuit has better frequency response as compared to the single tuned circuit. The use of double tuned offers the following advantage over single tuned circuit or amplifier. Bandwidth is also increased in double tuned circuit. Sensitivity, that means the ability to receive weak signal, is increased. Selectivity, that ability to discriminate against signal in adjacent band, is increased. So this is all about tuned amplifier. So if you have any question or doubt, please put in the comment box. Thank you.